What we're going to do right now is look at the American Gear Manufacturers Association AGMA gear design approach. It has three parts. First is the transmitted tangential load, WT, and then using several factors to modify that load to get WT modified. Then focusing on the bending stress and the fatigue criterion in bending, and then focusing on the contact stress and the pitting criterion. So by way of overview, the AGMA equations predict allowable stress and power transmission limits, and there's two main design perspectives. One is based on bending strength, and you can see in the pictures down below on the lower right the example of tooth root breakage. So that's an example of failure in bending. And secondly, contact strength. You can see on the lower left, pitting and wear, examples of failure due to insufficient contact strength in gears. There are modifying factors, including factors for geometry, material, size, speed, and load effects in the AGMA approach. It all starts with understanding what the transmitted tangential load is, and we're going to symbolize that with a W sub T. Force, W sub T, of course, is related to torque. So the force is the torque divided by the radius at the pitch circle. It's T times 2 over pitch diameter, D sub P. And then we're going to modify that with four factors, K sub 0, K sub V, K sub S, and K sub H for overload, dynamic, size, and load distribution factor. First off, of those four, the overload factor takes into account transient torque peaks. So not everything is always consistent, always running smoothly all the time. There's startup and shutdown. And during those cycles, there can be overload on the gear. So we've got a matrix of overload factors based on whether or not the power source is uniform, light shock, or medium shock, and whether or not the driven machine is uniform or moderate shock or heavy shock. You put those two together and you can get your overload factor. Secondly is the dynamic factor, K sub V, which has to do with how well the teeth were made for the gear and also how that interacts with the velocity, how quickly the teeth are hitting each other. So you see in this chart, there are two important variables. On the horizontal axis is the pitch line velocity, which I have feet per minute, and then I also have that translated to pitch line velocity in meters per second. And then there's various curves, and those are for the different quality levels according to AGMA. So 11 is a really good quality level, 5 is a bad quality level. So as you get to worse and worse quality levels, that dynamic factor K sub V goes up. Thirdly, we have the size factor, K sub S, which is worse for wider or thicker gears that could be less uniform in strength. There is a equation here, K sub S equals 1 plus the face width over 10 times the pitch diameter. Now, sometimes we need to solve for the face width. So if you don't know the face width, you can take an initial guess and start with assuming that the face width equals 0.4 times the pitch diameter. And so you get 1 plus 0.4 d sub p over 10 d sub p, and the d sub p's cancel. And so you can start by assuming a K sub S of 1.04. And lastly here is the load distribution factor, K sub M. It's also called C sub MF. And there are several effects embedded inside this load distribution factor. So there's 5 things in here. Let's look at each of these. Firstly is C sub MC. That is a factor for crowned versus uncrowned. You see an image here that's a sketch of crowned versus uncrowned. Crowning is where the teeth are rounded so that the location that needs more support has more support. And so when there's load, it flattens out and gives more uniform distribution of the loading. So crowning helps in terms of reducing negative aspects of the load. So you've got a value of 1, C sub MC of 1 for uncrowned teeth, and C sub MC of 0.8 for crowned teeth. Then you have C sub PF, which is a function of the face width and the module, so the relationship between those two variables. And if the face width is smaller than 430 millimeters, so that's 43 centimeters, so most gears are going to be smaller than that. That's a face width larger than 430 millimeters is very, very large. So that top equation gives you the C sub PF value. We're not done yet. We've got C sub PM, C sub MA, and C sub E. So let's keep going. C sub PM is a factor that accounts for the alignment. When we say alignment, we mean how well centered is the gear between the two bearings. So if the gear is in the exact center between the two bearings, then that factor C sub PM equals 1. If it's off center by too much, by more than 0.175, then that factor gets worse. So we have to take a value of 1.1 for that factor. The last two here are C sub E, and it's better for adjusted gears or lapped gears. Lapped means it's like very, very fine sanding, like buffing almost. So lapping is making sure that the gears are going to interface better. So you get a lower value, 0.8 for lapping. And then C sub MA is a function of how well the gears are made and how well they're going to survive. So you have 4 different curves. You can see them plotted on the next slide. So you can use the plot on the next slide to estimate C sub MA, or you can calculate it using the coefficients that are in the table based on which condition. Here's the curves for C sub MA, and those are the four modification factors for the load. So we can get W sub T mod by multiplying those 4 modification factors by the W sub T. Now we're going to use W sub T mod in 2 different equations. We're going to use it in the bending stress criterion, and we're going to use it in the contact stress criterion. So let's go first to bending. This is the bending stress and the associated fatigue criterion. You can see again, as a reminder, in the lower right, there's the potential for tooth root failure or tooth flank breakage if the bending stresses. So bending stress depends on the modified load, and then the face width, the transverse metric module, so that's the module for spur gears, the K sub B rim thickness factor, and Y sub J geometric factor for bending. Y sub J is related to the old Lewis factor and also incorporates stress concentration effects. The rim thickness factor only applies if the rim is less than 1.2 times the tooth height. If the rim of a gear, if it's a rimmed gear, if the rim of the gear gets too small, then instead of the tooth failing, the rim could fail. Then here's the geometric factor. This is a modification of the Lewis form factor, but also includes the accounting for stress concentration. So what you have to do with this chart is you take the number of teeth for one of your gears, let's say the pinion, and you go up to the plotted line for the number of teeth in the mating gear. And from there you get a geometric factor. The higher numbers are better. A really bad situation is when the load is applied at the tip of the tooth instead of pitch circle. That's going to shorten the life. But it looks like the more teeth that you have, the better in 2 aspects. One, all of these curves go up from left to right, so from less to more teeth. And also the mating gear curves go up from less to more teeth. So those are the geometry factors. Now, we looked at these 4 aspects. We looked at the load, 5 aspects: the face, the module, the K sub B, and the Y sub J, the geometry factor. Now, the criterion is that product must be less than the product of these factors. What are these factors? We've got the material bending strength, or as AGMA calls it, a stress number. We have the stress cycle fatigue factor, and this one's specifically for bending. A design safety factor, which must be greater than 1, of course. A temperature factor, which we can use 1 if we're at room temperature, or a well lubricated or well cooled gear. And then a reliability factor that we're familiar with. There's 2 different equations depending on if the reliability is less than 99% or greater than 99%. So the first of those is the material bending strength. This is the allowable stress number, essentially a type of strength from the AGMA. This chart is for US customary units, PSI, KSI, and then the SI units, megapascals, are over here. And you have a different equation for grade 1 than for grade 2. However, some materials are not through hardened. They're case hardened. So they're hardened more on the outside than they are on the inside using processes called nitriding or carburizing. Nitrided or carburized gears can have a higher hardness on the case where it matters. And so there's a table instead of a chart. There's a table here for grade 3. For example, carburized and hardened has the highest value listed on this table, 75,000 psi. That's the strength number, the stress number in bending. Then the stress cycle fatigue factor in bending, Looks a lot here like a fatigue curve. Starts out high, and then as you get more and more load cycles, it goes lower and lower and lower, and these values get really, really big. So it's on a log scale down here. And so this is 1 million, 10 million, 100 million, and over here behind my face would be, and then this line maybe would be 10 billion. Lots of cycles. The value here is 400 HB. HB is hardness Brinell. If you recall our Brinell hardness tester, that's exactly what we're talking about here. The Brinell hardness value for the gears. The harder it is, the longer it can last. All of those collapse, all those values collapse to about here at 10 to the 6th, between 10 to the 6th and 10 to the 7th, so between 1 million and 10 million cycles. And the location where they were constructed from was essentially 10 million cycles, 10 to the 7th. So if you have a gear that you're looking at that you're trying to get 10 million cycles out of, then your stress cycle vector is going to be 1. It's going to be less if you want more than 10 million. It's going to be more if you need less than 10 million cycles. Secondly, we have contact stress and pitting criterion. A couple images, only one's showing here, but pitting is definitely a failure mechanism for gears. And how do we prevent that? We prevent that by the following criteria. It's based on Hertzian load effects, where when you load one non-flat surface with another non-flat surface, there is a zone of stress that is extending to some depth underneath the surface. So the contact strength and pitting criterion starts with this Z sub E value, the elastic coefficient. And then you have a square root, and we put our familiar modified load in there, the WT value. We got our familiar face width in there. You have D sub W, which is the pinion working diameter. And then you have a couple other variables, which is first is the surface condition factor, second is the geometry factor. So let's look at those. The first one, the elastic coefficient. It depends on the relative elastic moduli and Poisson's ratio of the two elements. So rather than calculating all of those, they can be calculated for different materials, but some of those have been collected in a table, and we'll probably usually use that table because we'll be using familiar materials for these analyses. So what is the reason for the elastic coefficient? It's because a stiffer material produces a higher or a more localized Hertzian stress for the same geometry and load. So you have actually a contact stress penalty for a higher strength material because they localize that stress and they make it all focus in one point. Softer materials, they'll flatten more on contact, and so they distribute the stress more. So there's other disadvantages though to the softer material, but in terms of the elastic coefficient, the softer materials have the advantage. So the next slide is the table. Here's the table. It gives you elastic coefficients for different combinations. So for example, if I'm going steel gear with steel pinion, then I will use 2,300. The units here are square root PSI. Units in the parentheses are megapascals, square root megapascals. So if I'm going SI units, I'll use that one. Here's the geometry factor for pitting resistance. It's a function of the pressure angle, curvature, and speed ratio. So if I've got external gears, I have to use the top form. If I have internal gears, I have to use the bottom form here. When we say speed ratio, we mean either the ratio of the number of teeth of the gear to the pinion or the diameter of the gear to the pinion. That's the M sub G. This M sub N is 1 for spur gears. It varies for helical gears. We're going to focus on spur gears. Then we have to compare that calculated contact strength with the contact pitting criterion, which you see in the green on the right hand side, just like we did for the bending strength. And so S sub C is an allowable contact stress. Z sub N is a stress cycle factor for the contact. ZW, which is the same as CH, is 1 for a pinion gear. S sub H is a safety factor, it must be greater than 1. Again, we have Y theta for temperature and YZ for reliability, same as we had for bending. For the allowable contact stress, we have a similar plot, but very different numbers. So you have to watch out. The contact stress here, the allowable contact stress number in contact is very different from the bending stress. It's grade 2, grade 3, and we again have a table, or sorry, grade 2, grade 1. We again have a table for grade 3, including things like carburized and hardened gears over here on the right-hand column. And then we have a similar table for representing the effect of more and more and more load cycles. And again, it's normalized around 10 million. If you got 10 million, that's what the reliability data is based on. But if you're expecting more or less, you have to adjust that value. Then you have a hardness ratio factor, and this first plot of the two applies only if the pinion is through hardened steel. So a gear set lasts longer because a pinion usually has fewer teeth than the gear. If the pinion is harder than the gear, it usually lasts longer. So you can take a little bit of bonus through this hardness ratio factor if the pinion is a little bit harder. This first plot is for through hardened pinions. The second one here coming up, this plot is for surface hardened pinions. So you have the horizontal axis where you're going to find your hardness not of the pinion but of the gear, and then different curves that give you the surface finish of the pinion in micro inches. So 16 micro inch surface finish is a very fine surface finish for the pinion, and so that gives you a bonus, that gives you a boost in terms of contact and pitting life for the gear. And finally, here is how you can rearrange the equations. For example, if you want to solve for the minimum face width, you take the load, the modified load, the module, and the different factors, the different variables involved in bending fatigue, and in there is going to be the safety factor as well. And you can do the same thing rearranging the equation for pitting fatigue. And so given values for each of these constants and given a calculatable transmitted load here, you could calculate the bending fatigue, the face width based on bending fatigue criteria, and the face width based on pitting fatigue criteria. And then you could compare those two, and you can see which one gives you the minimum that you'll have to take. So whichever one gives you a larger minimum, because this says face width has to be greater than or equal to, that's what you have to go with. Because if you choose the smaller of the two, it's going to fail for the larger, the one that has the larger of the two minimums. So let's do an example of that here in the next video.